To finish off Chapter 15 today, we're going to be looking at a rather unique kind of problem. I know this is a large story problem, so let's just dive in. In April 2003, Science magazine reported on a new computer-based test for ovarian cancer. I'm not sure if this is the name of the test or the name of the article, but there we go. And this particular test examines a blood sample for the presence of certain patterns of proteins. So that's how we're going to determine if a woman has ovarian cancer. Ovarian cancer, though very dangerous, it's also very rare. It afflicts 1 of every 5,000 women. Okay, really rare. The test is highly sensitive, able to correctly detect the presence of ovarian cancer in 99.97% of women who have the disease. So if you have cancer, really good chance that they're going to spot it. However, it is unlikely to be used as a screening test in the general population because the test gave 5% false positive. Now, false positive is just what it sounds like. The test comes back positive, but that is false. It's not true. So you don't have cancer, but the test still is saying positive. Why are false positives such a big problem? That's what we're going to explore, because 5% false positive doesn't sound so bad. So to help us answer that question, here's what we're going to be doing. We're going to actually determine the probability that a woman who tests positive actually has ovarian cancer. Now, before we really break this down, see what that means, I want to show you how I like to organize a problem like this, because we have a lot of information and a lot of possibilities. So I like to design what's called a tree diagram. So I always start my tree diagram with a picture. We'll make this a woman here, some little curly hair there. And what could happen to this woman? Well, there really are 2 big possibilities. Either this woman has cancer or she does not. Okay, that's what could happen. And we'll go ahead and fill in some probabilities. What's the chance that a woman has cancer? Well, if we look back at our story problem, ovarian cancer happens in 1 out of every 5,000 women. 1 in every 5,000. So if I get that as a decimal, because again, I like decimals, I know your calculator is going to say this. Just type it in so you can see it for yourself. 2e minus 4. Well, there's no such thing as a probability of 2, and I know that 1 out of 5,000 is certainly not the same thing as 2. So just a quick reminder here about your scientific notation. This is the same as 2 times 10 to the minus 4. That's just your calculator writes it a little differently. So if I fill in the number 2, I'll put some decimals, some zeros behind. Right here's my decimal. That's the number 2. I'll put some zeros in front because I can. I put zeros wherever I want. They're just zeros. The minus 4 means I'm going to move the decimal place 4 in the minus or the negative direction. So 1, 2, 3, 4. So this is really 0.0002. Okay? I'm not going to do any more of those. So a quick reminder, scientific notation. So then what's the probability a woman does not have cancer? Well, it's everything else. So I could do 1 minus. So that's 0.9998. And if a woman has cancer, or if she does not, she's going to get tested. And 2 things could happen when you get tested. Either the test comes back positive or the test comes back negative. If you have no cancer, the test could still come back positive or negative. So let's go ahead and fill in some probabilities here. We read that if a woman has cancer, her test comes back positive 99.97% of the time. So again, I'm just switching that to a decimal. That means it's only going to come in negative 0.03% of the time. Okay, really rarely. And then we read about the false positive. So positive, false because they don't have cancer. There were 5% false positive, which means 95% of the time we get the right answer. You don't have cancer and your test comes back negative. All right, so here's our tree diagram. And what we're going to do is we're going to go ahead and multiply branches. Multiply branches. I want to know what's the probability a woman has cancer and tests positive. And tells us we're going to multiply. So we'll just multiply those together. And this is what I got, 0.00019. And I could do what's the probability a woman has cancer and tests negative. Whew, that's 7 zeros, really small chance. And I went ahead and I finished all this. So here are my results from my tree diagram. Now I haven't actually talked about the question. This was my way to get organized, make sense of all my information. So let's go back and take a look at what we're really being asked to do. Okay, we're done with scientific notation. I've underlined in blue here what we're being asked to do. Determine the probability that a woman who tests positive actually has cancer. So they've given us two pieces of information here. The woman who, excuse me, I wanted to highlight that in red. A woman who tests positive actually has the cancer. So I've got two pieces of information. Well, they tell me that the woman is testing positive. So this is a given. This is a condition. I know this already. Given that a woman tests positive. I know that has happened. The woman tests positive. So what's the probability they actually have cancer? So I'm looking for the probability a woman has cancer given she tested positive. Now I just want to remind you that we did have a formula for these conditional probabilities. We took the probability of and we divided by the probability of the second piece, or the given. So I'm going to use that here. This is going to be the probability of cancer and positive, and I'm going to divide that by the probability of positive. So let's take that over onto our next page where we have all those probabilities. All right, so I might have to slide this up and down just a little bit, but a reminder, we're doing probability a woman has cancer given she tested positive. And in order to do that, I'm going to find the probability a woman has cancer and test positive, and I'm going to divide that by the probability of just testing positive. I don't know whether they have cancer or not. So, probability of cancer and positive. Wow, that's the one I just covered up. Okay, here, this was probability of cancer and testing positive. So here is my result. I even already multiplied it. Beautiful. So that's going to go on top, 0.00019. Now I need to divide by the probability of testing positive. The thing that we have to watch out for is there's actually two situations where you tested positive. You can test positive if you have cancer, or, big clue there, you can test positive if you don't have cancer. So these people test positive, or these people test positive. Because you can't be both. You either test positive with cancer or without. Or tells us we're going to add. So let's take that underlined in green, 0.00019. We're going to add, or means add, 0.04999. Now you might want to put parentheses around that on the bottom. Go ahead and type that in your calculator, and let's see what we get. All right, I got 0.003, I'll round that to 8. Wow, what does that mean? Well, let's write that as a percent. That's 0.38%. That is less than 1%. That's less than 0.5%. Let's go back to the question. Suppose I know a woman tested positive. What's the chance she actually has cancer? Less than 1%. That means more than 99% of women who are testing positive don't really have cancer. Wow. So why are false positives such a big problem for this test? Because most women who are testing positive, it's a false positive. Amazing. Tree diagrams teach us really some interesting situations. We get some unexpected results. It sounded like a really great test, but it turns out most women who are taking this test and test positive, only 0.38% of them really have cancer. Crazy.